So it's been a while. Let's see, I got this.
It has.
How's math going for you?
Pretty good. I'm understanding most of it, except these few problems that I had sent to you.
Okay. What year are you in now?
I'm a junior.
Okay. And you're taking Algebra 2?
Algebra 2.
Okay.
Yeah.
All right. Well, if we look at this first problem, looks like you've tried to solve it using matrices.
Yes.
Okay. Notice that the result you came up with, which was 8 and minus 3, if you plug that into this equation right here, it's 24 minus 3 does not equal 5.
Okay.
Okay? And you don't want to miss part A, because if you miss part A, you are missing part B. Now, let's talk about a couple of ways to solve this system of equations. I don't see any instructions that say that you have to solve it by using matrices.
No.
Well, those aren't the easiest way to solve it. The easiest way to solve it is by elimination.
Okay.
Remember the two methods you have, which are substitution and elimination?
Mm-hmm.
Well, what would we need to do to one of these equations in order for us to be able to eliminate a variable?
Would be, let's see.
Let's call that equation 1 and that equation 2. You can always add or subtract equations. Unfortunately, if I add or subtract these two like they are, I'll still have two variables. And my goal is to get it down to one variable only. So, what could I do to equation number 1?
Could you multiply or
By what? Yes.
-1?
No? How about by 4?
By 4, okay.
Huh?
Oh, right, for the y.
Well, notice what that makes. If I take equation 1 and multiply it by 4, I get this as a new equation 1. You see that?
Mm-hmm.
So all I've done is multiplied every single term by 4. And you're always allowed to do that in algebra. You can do whatever you want to the left side as long as you do it to the right side.
Okay.
Now I have two equations which, if I add together, the y variable will disappear. That's what I want, because then that'll
Okay.
be one equation with x only. So what happens if I add these two equations? And remember, you can always add or subtract any two equations, no matter what they are.
If you add it, you get 17x equals 17, and then divide 17 on both sides and you get 1.
So x equals 1. Now, how do you solve for y?
Plug in 1 for x.
Into which equation?
You can do it to either one, or do it to the 5x minus 4y.
Always do it to the simplest one. Actually, that's the original one that we had before we manipulated it. What is y? You can probably do that in your head. If you plug in x for 1, what does y have to be?
Would be 2.
Yeah. Always work with the simplest equation. And the only reason this was simple is because it had nothing but small numbers. This also had small numbers. That would have been okay, but it had a negative number. This had big numbers. We would not have wanted to work with that. Just kind of a rule of math. Always work with the smallest numbers you possibly can. And
Okay.
that's your solution. So what we want to write here is 1, 2.
Okay.
What's the product of x and y?
2.
Right. Now, you chose to do it with matrices. Do you need to know how to do it? I've looked at the rest of your problems. I do not see anything that says solve it using Kramer's rule. I can go through Kramer's rule with you if you like to come up with this same solution of x equal 1, y equal 2. But I don't know if we want to spend the time doing that if you don't have to know how to do it.
Yeah, we didn't even really talk about that.
All right, then don't use Kramer's rule on this problem. In other words, this is very straightforward. This is very solvable by the rules you have been taught for the last 3 years, which is solving a system of equations by elimination. Solve the following quadratic. What's the first thing we have to do in order to solve a quadratic?
Well, I split the 3 different terms into A, B, and C.
Aha, but they're not A, B, and C the way they currently are. They're only A, B, and C.
They are A.
After you get everything on one side, then they are A, B, and C. At the moment, you got this on the wrong side. In other words, A, B, and C only applies to standard format.
Okay.
Once you get it in this format, then you can figure out what A, B, and C is. But not before. So what do I have to do to this to get it in that standard format?
You would subtract 31x.
Yeah, and I'm going to put it in the middle so that I order all of my polynomials correctly. Now it's in standard format. Now you can say A equals 7, B equals minus 31, and C equals minus 20. You see the difference. You had B probably equal to 31 instead of negative 31. Although, I don't know. I don't see that here. Ah, I see what you did. You called that A and this B. B, for reference purposes, A is always the coefficient of the x squared term. In other words, whenever you have a quadratic, you have an x squared term, you have an x term, and you have a constant. A is the coefficient of the x squared term. B is the coefficient of the x term, and C is the constant. So you have to get everything in standard format, and then you can just read A, B, and C. Okay, so now tell me what x is, given that A, B, and C that we have. What's the standard general format for the quadratic?
Negative b plus or minus the square root of b squared minus 4ac all over 2a.
Okay, that's pretty good. Were you reading that, or was that from memory?
Oh, I memorized that one.
Good, good. That's a good one to know. You're going to need it several times. So what's minus b?
Negative 31.
No, b is negative 31.
Oh, so it'd be positive
Yeah.
31?
Well, in other words, when you take a minus of a minus, it turns positive. In other words, if b was 31, then minus b would clearly be minus 31. Well, you can't have it to be the same thing. So if b is minus 31, then minus b has to be 31. Now, b squared is minus 31 squared. I have no idea what that number is. And the best way to do this is to just plug in just exactly like I'm doing here. Now, be very careful of this term right here. I've had many, many students mistake that for subtract 20. You know what I'm saying?
Mm-hmm.
That is not subtract 20. It's always 4 times A times C. So you're subtracting 4 times 7 times a minus 20, which is like minus 560. But it's a potential problem because we all write it like this. And if you make your minus sign too big, it's very easy to misread it and think that it's minus 20. Well, whenever you're dealing with the discriminant, which is everything inside this radical, it's never minus anything. It's always the product of these three things. So you want to kind of get used to that.
Okay.
In other words, don't make that mistake more than once. Okay? So, what do we have here? Let's simplify it. Tell me what we have. Do you have a calculator?
31. Yes, I do.
Okay, good. So we have 31 plus or minus. What is the square of 31?
961.
You notice I didn't ask whether it was minus 31 or plus because it's the same thing for both. In other words, when you square minus 31, you get a plus 961. When you square 31, you get a plus 961. All right, and let's see, this was 80 times 7, that's 560, and it is a minus of a minus.
So it becomes a positive.
Yeah, and then this is 14. So, continuing simplification, what is
So then
that number right there?
1,521.
Okay. Now, there's your two answers. The question is can that be simplified?
The square root of 150 or 1,521 is 39, so it can be.
Yeah. You know how I knew that it could be? Is that these digits add to 9. If you add the digits of any number and it adds to 9, then that number is divisible by 9. And if it's divisible by 9, I can break this up into square root of 9 times square root of whatever the result is. You apparently put it in your calculator. What'd you get?
39.
Okay. So now what are our two answers? Solve the following quadratics. We need two answers.
So 31 plus 39 is 70 divided by 14, and that's 5. So one of the answers is going to be x equals 5. And then the other answer is going to be 31 minus 39, and that's negative 8 divided by 14, and that's going to be negative 0.57, or...
Better to put it as a fraction. The reason it's better to state it as a fraction is because that guarantees precision. If you give me the decimal value of that, you're rounding it off. So the best answer for this test is 5 and minus 4/7. All right, let's look at B. Again, it just says solve, so we can solve it however we like. How would you solve this?
Well, what I did first, which I think might have been wrong, is for the square root, or the square of x minus 2, I put 2 of them, so I did 4 times x minus 2.
I see what you've written here, and that's absolutely correct.
Okay.
Okay? So it really is 4 times x minus 4x plus 4. Notice that I squared the x minus 2.
Oh, goodness.
Huh? That's what you did. You squared it also. You just didn't simplify it. In other words, you got minus 2x minus another 2x. Well, that's minus 4x. Let's talk about that process for a moment. If I am squaring a plus b, instead of having to FOIL this every time, you know, you could FOIL it and you get this every time you FOIL it. And then you simplify it and you get this. Well, this is a process that you have to do so frequently that it's worth memorizing. It's that. And a minus b squared is very similar, only it's this. In other words, don't waste time foiling it every time. You know instantly, the moment you see an a plus b squared or an a minus b squared, you can translate it into that. That's how I did it as quickly as I did, is that I immediately made it x minus 4x plus 4, which is what that would simplify to. Now, it looks like you got your parentheses a little confused. You needed a parentheses right here, and then you'd have been fine. Without that second parentheses, it looks like you get kind of confused.
Yeah.
Well, let's go back to this and see what happens. So that minus 6 belongs over there. Now, the best way to solve this, well, you know what? All right, let's solve it like this, and then I'm going to show you a way that's actually a little easier. So what's the next step here?
You could either multiply 4 or you could add 6 on both sides.
You have to multiply the 4 first. Remember your PEMDAS. Well, no, you're right.
Okay.
You can multiply we'll add 6 to both sides. How's that? Okay? And then that gives me this. In other words, I'm distributing the 4. This is not the easy way to do it, but it's one way to do it. Okay? Now I'm going to set it up as a normal looking quadratic where I have 0 on one side, and I'm going to do that by subtracting 36 from both sides. So I end up with 4x squared minus 16x minus 20. Now, there's a greatest common factor of 4, and I can take it out. Now I can divide both sides by 4, leaving that. And now I can factor this thing. How does this thing factor?
I
think you were the one that taught me the California method. I have a video recording of you telling me the California method. Is that correct?
Oh, I have no clue.
Pretty sure, from 2 years ago or 1 year ago. And I have yet to use it since. That's because it's a horrible method. It's not the best method to use. The method I use is that when you get to this quadratic, you examine the sign on the constant, which is 5, and the sign is negative, means the signs have to be opposite. Now you're looking for factors of 5 that subtract, because of that negative sign, to the number 4. Well, that's 5 and 1. So your solutions are what?
So it'd be x equals 1 and x equals negative 5.
No, it's a little...
Oh, it'd be opposite because it'd be x minus 1 and x equals positive 5.
Okay. So there's the hard way to get it, which is to expand everything, get it into a quadratic, factor the quadratic, and get your answer. Let me show you an easier way to do this problem. And I've become a true believer in doing problems multiple ways. It's the Asian way. The Asians lead the world in mathematics. What's the first step here? You wanted to do it when I was talking about it originally.
Split up the x minus 2 into 2
Don't
parts.
do that.
Add 6.
Yeah. If I was going to do that, then I get to this step. Now what's the next step?
You could divide by 4
There you go.
on both sides.
And this gives me this. Now what can I do?
Now you could split up the 2 equations.
No, still don't want to do that. How about if I take the square root of both sides?
Okay.
What's the square root of the right side?
3. Oh, sorry. No, it's
If you take the square root of x squared, you get x. If you take the square root of the quantity x minus 2 squared, you get x minus 2. In other words, whatever is inside, and it's being squared, and you take the square root of it, you get z. That's the beauty of doing it this way, is that you automatically can get rid of the quadratic because you take the square root of it and you're left with this. Now, the problem with this method is that most people make a mistake when they take the square root of 9. What's the square root of 9?
3.
It's plus or minus 3. Notice why. Minus 3
So we're
times,
solving for
well, minus 3 times minus 3 is 9. So is plus 3 times plus 3. That's also 9. So both of these are 9 when you square it. That's why you always have to have the plus or minus. So I don't know how to get students to remember this. I wish there was a little song like they have for the quadratic formula, but 90% of the students forget the plus or minus. And the only thing I have to tell students is that whenever you're taking the square root of both sides of an equation, start your answer with plus or minus. Doesn't work that well, but nonetheless, that's what I tell them. I still get everybody that forgets it. Okay, you see how I get to that step?
Uh-huh.
Now, what are my two answers for x?
-5 and +5.
No, not -5. In other words, the first answer is that, plus 3 plus 2, so there's 5. The next answer is the negative.
-1.
Yeah, exactly. That's the same answer we got when we did it the first time. But we did it a completely different way. Now,
Yeah, and it was a lot easier.
it was a lot easier, but it's also much easier to make the mistake. Notice that when we did it this way, we got these two answers, and there was no other way to get anything but those two answers. When we did it the easier way, we could easily have made a mistake and left off the plus or minus. And if you leave off the plus or minus, let's say I erase that, well, you get only one answer, x equals 5. So if you do it the easy way and you forget that plus or minus, you're going to miss one of your answers and you're going to lose half credit on this problem. So always remember, when you're taking shortcut methods, you have to do it perfect. Whereas if I do it the long way, I don't have to do it perfect. I'm going to get this x equal -1, x equal 5 regardless. All right. Have you recently had matrices?
Not very recently. We didn't do too much with them.
Because I'm curious as to why you attempted to solve that using matrices. There's nothing wrong with using matrices to solve systems of equations. The problem is that when you have just two equations and only two variables, it's really much easier to solve it by elimination than using a matrice. Where matrices are very valuable is when you have a lot of variables and a lot of equations. I don't know if you've ever tried to solve 3 equations and 3 variables. It gets exponentially harder.
Okay.
If I were to try to solve 4 variables and 4 equations, that would be extremely difficult. That's where matrices come into play. Matrices are extremely valuable if you have a lot of variables and a lot of equations. Let's say you're trying to solve a weather front, and there are 56 variables and 56 different equations. Well, if I tried to do that by hand, it would take me probably a month. But if I can set it up as a matrix, I can solve it in a computer very rapidly. So matrices are beautiful for solving multiple equations with lots of variables. If you only have 2 equations and 2 variables, then just solve it the normal way using elimination, unless they specifically say solve this using Kramer's rule. It'll be much easier and more accurate.
Okay.
Solve the following system for x and y. Okay, again, we just have two equations, two unknowns. But this time it's a little different. That's in standard format. But the second one is not in standard format. When one of your equations is not in standard format, what's the best thing to do? In terms of a method of solving it. You have two choices.
Change it to standard format?
Well, you could do that. Yeah, that works. But there's another method besides elimination. What is it called?
Substitution?
Yeah. And you use substitution whenever one of your equations is already defined as one variable. In other words, we already have y completely defined here. So,
okay.
What I've always felt is that when you have this situation, your best method of solution is substitution. Well, how are we going to do it, substitution?
Substitute y in for y.
Yeah, substitute y into the first equation. So the first equation becomes what?
So it'll become 2x minus 3 times x minus 1.
Make sure you put that in parentheses. That parentheses is huge. If you omit the parentheses here, you're going to get the wrong answer. So whenever you have a question as to whether to use parentheses or not, use them. You can never go wrong using parentheses. You can frequently go wrong by not using them. Okay, now we have one equation and only one unknown, x. That means we can solve it. So let's solve it. What's my next line?
So you could multiply negative 3 and distribute negative 3.
Give me the next line.
Minus 3x plus 3 equals negative 1.
Good. The next line?
And then you subtract 3, so then 2x minus 3x equals negative 4. And then you have 2x minus 3x, so that becomes negative 1x.
Okay.
Equals negative 4. And then divide by negative 1 on both sides. And then that becomes x equals 4.
Okay, if x equals 4, what's y equal to?
3.
Okay. Good. You've been making some advancement in your math skills. That's good to see.
Thank you.
All right. So, B doesn't make any sense. They've already asked you for solve it for x and y, and we did so. So, I'm not sure what the purpose of that thing is there. Let me pull up the next page. Did you just send me 2 pages is all?
Well, I had sent them before. They might have gotten delayed a little bit.
Yeah, I thought I saw another email come in. I wasn't sure. Well, let's cover everything I've got, and then if we still need more material, I'll go look for more emails.
All right.
How can I solve 19?
I have no clue on this one. This one always gets me.
Okay. She can drive 73 miles in 68 minutes. Well, what they want is give this solution in miles per hour. Well, I already have miles in the numerator, So it's all I have to do is convert the denominator to hours. Well, what's the conversion rate? Minutes to hours.
60.
60 minutes per hour. Now, pay attention to the units here, because the units are what solves it for you. In other words, the whole goal is to convert it to miles in the numerator, hours in the denominator, so I know I have the right conversion factor because the minutes cancel. What am I left with? Miles per hour. So I have 73 times 60 divided by 68, and the units are going to be miles per hour, which is what they've asked for. So whatever that number is, there is your answer.
So the top number is going to be 4,380, and then divided by 68 equals 64.41.
Miles per hour. That was her average speed.
That was easier than I thought it was.
Yeah, it was much easier actually, probably. In other words, whenever you're doing a units conversion, sometimes they might give this to you in seconds. In other words, they would say 3980 seconds. Let's go through that. 73 miles per 3980 seconds. They're not ever going to give this to you like this, but let's say they did. Well, how do we convert that to miles per hour? Well, we need hours in the denominator, so first of all, let's multiply it by 60 minutes per hour. But now, if I do this, I'll have miles per second hours. So I need another conversion factor. How about 60 seconds per minute? And notice what this allows me to do. Cancel the minutes, cancel the seconds, and I'm left with miles per hour. So it'd be 73 times 60 times 60 all over 3980, and my units are going to be miles per hour. So the secret to converting units is always to just figure out what the conversion ratio is and make sure you have it in the right order. In other words, if this started out hours and they were asking about miles per second, then I'd want to say 1 hour per 60 minutes and 1 minute per 60 seconds. So these conversion ratios depend on which unit you're trying to lose and which unit you're trying to end up with. You see what I'm saying?
Mm-hmm.
Number 20. What kind of calculator do you have, Mia?
I have a TA 83 plus.
An 82 plus?
83 plus.
83 plus. Do you know how to do linear regression on it?
Okay, let's see. I do just, hold on 1 second.
All right, hold on. Before you do it, I've done it in Wolfram Alpha. Remember Wolfram Alpha?
No.
From previous sessions? I've probably used it before with you. Wolfram Alpha is like your best ever calculator. Much better than your TI-83 Plus, better than the Inspire. In Wolfram Alpha, you can put in a set of numbers, much like this table. This table is a bunch of XY values, right?
Mm-hmm.
They would tell you to use this for X, use this for Y. You're going to go into your calculator, you're going to make two lists, top row is the first list, second row is the second list. Once you get those two lists in there, then you're going to go request that your calculator do a linear regression of those two lists. This is what you get when you do that. Now, notice what linear regression is. In other words, each of these red dots represents one of these values. Notice that I have 1400, 245. So if I go to the 1400 on the x-axis, that's 245. The next point, 1600, 312. Well, if I go to 1600, there's 1600 and there's 312. So I have a bunch of red dots that correspond to all of these xy values. And if you put all of these xy values into two lists and did a scatter plot, this is what you would see without the line. In other words, if you just did a scatter plot, you would only see the red dots here, which is a straight plot of these xy values. Now, the trick is to assume that there is a straight line that fits nicely between those dots. Let's talk about that for a minute. If I gave you a bunch of dots like this, you would say, wow, that looks linear. In other words, I could draw a straight line through those, and that's a pretty good fit, right?
Mm-hmm.
Okay. What if I had a bunch of dots like this? Now, I could still draw a straight line, but it's not as good a fit, right?
No.
No, not at all. That's what R squared measures. When you come up with a linear regression and it gives you a value for R and R squared, that is the measure of the quality of fit. This is a bad fit. Let me show you a good fit. If I draw a straight line through that, it's almost a perfect fit, right?
Mm-hmm.
That would have an R squared value of very close to 1. A bad fit has, in other words, that's the best fit, is 1. A bad fit might have 0.5. In other words, if my dots were very far away from that line, that's not the greatest linear fit. And that is measured by this R value. So once you request your calculator, and it's only a calculator that can do this, once you request your calculator to come up with the equation of this line, it's also going to give you a measurement of how good of a fit it is. In other words, if all of the dots are lined up very much in a straight line, it's going to be a very good fit. You're going to have a very high value of R. If the dots are really spread out and hardly even look like a straight line, but I can still put a straight line through it, that's a low value of R. So, what do you get when you input into your calculator this table of lists? Your calculator gives you M and it gives you B. Let's say your calculator says M is minus 3.178 and B is 14.96. That means the equation of best fit is this. And this is what your calculator is going to give you. It's not going to give you what I have in a square here, or a rectangle. In other words, it gives you M and it gives you B. Now, let's go to Wolfram Alpha, because I've already done this in advance. I put in the table that's from your homework, and it gave me this equation right here. Well, Wolfram Alpha does it a little bit better. They tell you that they give it to you in y equal mx plus b format. In other words, the slope is 0.147652. The y-intercept is 41.3769. They show you a graph of it, and they give you the value of r. Notice that they give you r squared is 0.768. Well, that's not 1, but it's also not 0.5. In other words, if we look at this collection of red points here, we can see that this line does a fairly good job of approximating those points. Not a perfect job, not as perfect as if all the points lay in a straight line. Then our r would be 1. But good enough that we get a decent r. And they give you r squared, which is more accurate. And r squared is 0.76 for this function. Now, here's the thing, is that right now we're doing linear regression, right?
Mm-hmm.
If I give you that collection of dots right there, the linear regression would be something that looks like that, right?
Yes.
Now, you can do other regressions besides linear. You can do quadratic, which are parabolic. And guess what? If I do a quadratic regression here, what kind of r squared am I going to get if I do a quadratic regression? A great one. R squared is going to be almost equal to 1. Because every dot fits this parabola. It doesn't fit the linear regression at all. But it fits the quadratic regression beautifully. So the mathematician has to decide which one should be applied to a given set of data. Well, here, one would expect that the square footage versus price of a house would be linear, not quadratic. In other words, we would expect that to be relatively straight. Those data points are going to be around that straight line. The more square footage you have in your house, the higher it's going to sell for. It's going to look like that. We wouldn't expect it to look quadratic. We would expect it to be linear. So we would apply a linear regression to that set of points. And that's what they've asked you to do here. Write a linear regression equation. Now, since I've done it, if you want to use my results, you're welcome to. This is the equation right here. You want to write y equals that. That's your answer.
Okay.
Is this equation reliable? Well, that has everything to do with the value of r squared. If r squared is very close to 1, then the equation is very reliable. And what they mean by reliable is it an adequate predictor of, say, a 4,000 square foot house. Notice that every house in their list is less than 2450. Well, that's a relatively small house. I would venture to guess that you live in a house bigger than that. So, could you use the equation we came up with to predict what the price of a house would be if it was 5,000 square feet?
Yes.
Well, you could use it, but how good of a predictor would it be? Well, everything is based on this R. I'd be stretching it to I would say that not that great of a predictor. Because notice that this line is very much based on these two extreme values up here. If those values weren't there, this line would have a different slope, depending on where they were. So that's why R here is not that great. It's 0.768. So I'm not sure what they want as an answer here. It's not because it came straight from the, whatever that word is. The reliability of the equation has everything to do with R, the correlation coefficient. And our correlation coefficient was mediocre. It was 0.768. I don't know if that's good or bad, to be honest. So I don't know if the answer is yes or no, but the answer should be yes, because the correlation coefficient was 0.768.
Okay.
So, if we use the equation that we have, which is still on my screen here, to predict how much you would expect to spend on a house that has 2,000 square feet, how are we going to do that?
Would you plug it in for X? Would you plug 2,000 in for X?
Yeah. So we have 0.1476 times 2,000 plus 41.3769. What is that? That is 2952 with 3 zeros, meaning there, plus 4.37. So it looks like we would pay about $300,000 for a house that had 2,000 square feet. Now let's just look at that. Hold on. If I go to 2,000 square feet on the graph and go up, I must have done my math wrong, but this is not exact math here. In other words, when we come up with a line that is the least fit, we're coming up kind of with an approximation. Let me think I did my math wrong, though. Did I do my math right? 0.295 with 3 zeros would make it 295,000 plus 41. I left off the 1 there. That makes it 336,000, and that fits our curve. If we go to 2,000 square feet and go up, we are at about 336,000 there. So I was wondering why it didn't fit with my answer, and that's because I had dropped a 1 when I was doing my answer. All right, so that answers C. All right, so we've gone through the first 2 pages, and we have like 4 minutes to go. Let me see if I got your other page.
That last one was just kind of an extra one, so if you don't have time to do that one, that's fine.
Is that what I'm looking at here? Is the full-size render?
Yeah.
take a quick look at it. We'll see how big of a problem it might be here. Okay, to graph that, you need to do it on your calculator. I don't think they expect you to be able to graph that manually. Although graphing manually isn't that hard, you can always make up values for x, figure out what s is, make up a table of values, and plot those points and connect them with a line.
Oh, okay. Yeah, this problem's pretty easy.
Well, yeah, I suspect they want you to just put this into your calculator. In other words, y1 equals this. And see what it graphs at. Identify any turning points on the domain. What real-life meaning do these points have? Well, what they're talking about is this. This is y. This is x. And I've graphed the function, an approximation of. I have no idea what the function graphs at, but a typical cubic has one little loop in it, like that. Well, they said graph any turning points. Well, there's a turning point, and there is a turning point. Notice it turns from going up to going down, and then it turns from going down to going up. That becomes very important in higher mathematics. What real-life meanings do these have? Well, the real-life meaning of this would be that 40 years after 1960, in other words, from 1960 to 2000, the enrollment did nothing but increase. And then from the year 2000 to 2001, it decreased. And then from 2001 through current, it increased again. So that's what that would mean. Now, I don't know that 2000 and 2001 are the right numbers. I don't know that at all. You'd have to graph this function. Once you graph it, you'll know where the thing turns.
Okay.
When they say what is the range of the function, that merely means the y values. In other words, if I said what's the range of this function, it's 0 to whatever that value is at the top. And it's going to stop because they only go from 1960 to 2001. So their graph is going to stop at 2001. In other words, their graph may look like that, in which case the range would be from 0 to there, whatever this value is right here. The domain would be from here to here. All right. That's a good place to stop. I hope I haven't overwhelmed you with information. We covered quite a bit tonight.
No, you're good. Thank you.
All right. You're welcome, Mia. I'll talk to you next time.
All right. Bye.
Bye-bye.